the structure of molecules based on the Lewis dot diagrams that we can predict for them. So it's pretty nice. We're going to look at that right now. If you look at a Lewis dot diagram for water as an example, it looks like it's this linear thing, right? And it looks symmetrical. And this thing about symmetrical things is that, well, they would have no poles, right? If the things were symmetrical, that means, think about it from a mechanics point of view. If this weighs as much as this weighs, it kind of cancels itself out. And so I don't have a pole. And if I have no pole, that means water acts like a symmetrical molecule, like a non-polar molecule. And non-polar molecules have very weak interactions with one another. And so based on this, you would erroneously think that water is symmetrical. It is not. So let's look at what these things actually look like. And the theory behind this is called the valence shell electron pair repulsion, or VESPR for short. We're going to call it VSEPR. And it's going to basically predict what things look like. And so the few slides I have right now is just going to give you the quick general overview, and then we're going to go over a bunch of examples that will hopefully show you how to do this quickly. Okay, so what actual electrons do in a molecule is they try to stay away from each other's way as much as possible, because, as you remember, two negatives do not like one another. So same charges repel, and they're trying to stay away from one another's way. All right, we're going to call a group either lone pairs, lone electrons, or shared pairs, so bonds. Okay, so these are lone pairs. You can have a bond, a double bond, a single bond, or triple bond, or you can have single electrons, like the one that's here on nitrogen. Okay, so as I said, atoms try to stay away from one another as far as possible. This is a really good demonstration with balloons. You can do it yourselves. If you get two balloons together, they try to stay away from each other's way, so they will go to opposite ways. The same thing would happen when two atoms get together. They will generally look like this, like a linear type thing. Okay. When you have three of them, it will look like what we call trigonal planar. It will form a plane above that. You can put a surface here, right, and it would be level. That would mean by trigonal planar. And the angle between each one of the circles here will be 120 degrees, like like in the outside of the triangle. To get to 360 around the circle. All right. And so if you have four of them, you form this tetrahedral type shape. You can see that. And this is symmetrical. You flip it any which way. Same here. You flip it any which way, they all look the same. All right, so if I flip it over to the side, it will look exactly the same. If I have five, it will form this thing called trigonal bipyramidal. And if I have six, it will form octahedral. These two are not going to be encountered as often. I'll show you some examples of this, but these three are the ones you're going to see the most. All right. So how are we going to determine the molecular shape? All right. So what we're going to do is, this is a recipe for it. You're going to draw the Lewis structure for the molecule. Around the central atom, you're going to count stuff. All right. You're going to count domains. And domains are single bonds, double bonds, triple bonds, and lone pairs. Okay, this will determine the electron geometry. I'll show you in a second. This will all make sense, I promise. With the examples, are going to make a whole bunch of sense. Okay, around the central atom, you also want to count bonding domains and non-bonding domains, which is basically you take this domains and you split into two. So bonds count as bonding domains, and lone pairs count as non-bonding domains. So the bonding domains equal this plus this plus this, and non-bonding domains equals just the lone pairs, and if you have lone electrons, stick them in there, why not? This will determine the actual geometry of the molecule. Okay, so you'll have domains, bonding domains, non-bonding domains. You just count them. Put domains, bonding domains, non-bonding domains, and then you look at a table. And let's look at a bunch of tables. If I have two bonding domains, if I have two domains total, the electrons will look like this. If I split this into bonding and non-bonding and I get 2 and 0, the molecule will be linear. Here's an example. Carbon dioxide will look like this. And I'll show you examples how to get to it. If I have 3 domains, the electrons will kind of follow this structure. If I split the domains into bonding and non-bonding, if it's 3, 0, the molecule will also look like this. If I have 2 and 1, the molecule won't. The molecule, this is not an atom here. Like this, see that? So these electrons are going to make sure that these two are sticking down and they don't look like this. So even though NO2 looks like CO2, NO2 minus is not linear, it's bent. Okay, and that's what happens with water here. Okay, so if I have 4 bonding domains, I can split this into 4 and 0. 4 and 0 is tetrahedral, like we already showed. If I'm missing one of the atoms, as in it's going to be a non-bonding, this thing is going to push the other 3 down. So in the case of ammonia, this is what happens. And so ammonia is not going to be this linear thing. It's going to have 1, 2, and 3 going down. And if I have water, well, I have 2 pairs of electrons that are actually pushing the other 2 hydrogens away from the center, and this does not look like CO2. This is a bent structure, and so this is not symmetrical in a sense that I can't just cancel the 2 wings out as easily. All right. All right. So if I have 5 domains, my electrons look like this, and then I can count along and get trigonal bipyramidal, seesaw, T-shaped, or linear. So this looks exactly like this. Just happens to be because of the way it works out. Okay. And octahedral, I will get these. I can get octahedral, I can get square pyramidal, and I can get square planar. Okay, so this is a whole bunch of these things. So let's look at examples. Okay, and we'll do a whole bunch of examples. Hopefully it will be clear at the end of all of this. Okay, I have a bunch. So predict the geometry for the following. We'll do that. We'll do for, so let's do the VSEPR geometry for, I think it's 3 or 4 that I have here, or something like that. All right, so this is not centered. I don't know why it keeps moving. Okay, so ASH3. Okay, so I need to draw the Lewis dot diagram first. So how do we do that? Let's use this as a practice to do that. Okay, so I need 1 for the Lewis dot structure again. I need total valence electrons. And from AS I get 5, and from H I get 1, and there's 3 of them. I add that up and I get 8. Okay. Now I'm going to draw the skeletal structure with the central one somewhere. So it's probably going to be the AS because the H's, there's 3 of them. So I'll put AS in the center and I'll put 3 H's around it like this. Now the rule says take the 8, distribute them so that the wings get octet. All right. Remember, hydrogen is an exception. Hydrogen only wants 2. So I will put 1, 2, 1, 2, 1, 2. Okay, so I put 6. And so now, I'm sorry, I'm going to put them so that they share. I have 2 left over, put them in the center. So I have that. And so this becomes H, AS, H, H, like this. Okay, so this is what this looks like. All right. Now, I'm going to look at the central atom. And I'm going to do a bunch of counting. So domains equals number of single bonds plus number of double bonds plus number of triple bonds plus lone pairs. Number of lone pairs. Okay, so how many do I have? Well, I have 3 single bonds. I have 0 double bonds. I have 0 triple bonds. and I have one lone pair. So my domain is 4. Okay, so let me go back to those tables here. Look at the electron, look at the domains. 5, this is 6 here, so I'm looking for 4. So, okay, so my electron thing is going to be tetrahedral. My goal now is to look to see whether it's going to be this, this, or this. All right. So, all right, so I know that my electron geometry is tetrahedral. Great. Now, I want to determine my molecular geometry. That's the more important thing to me. So I'm going to look at bonding domains. Those are just the number of single bonds plus number of double bonds plus number of triple bonds. So I have 1, 2, 3 single bonds plus 0 plus 0. So this is 3. And then I have non-bonding domains. So it's just this is pretty silly. It's just basically counting, isn't it? Once you do the Lewis dot diagram. So now the non-bonding domains, this is just number of lone pairs. So I have, if you look at here, 1. So I have 1. So I go back to the table here. I have 3 bonding domains and 1 non-bonding domain, meaning this is what it's going to look like. This is going to be trigonal pyramidal. And that's how you, if the question asks you what's the molecular structure, it's going to be trigonal pyramidal. And we probably wouldn't ask you to draw it, but it would look sort of like this. This is sticking out kind of thing. Okay, and I have like these two at the top. I don't have to draw that, but basically this thing is sticking out, sort of like imagine this coming towards you. And so it's sort of like symmetrical around that, and then these electrons push it down, so there's some sort of an angle, like the balloons did before. This pushes it less than an atom would have, which is why it's not a symmetrical molecule, necessarily. Okay, so, all right. So that's one example. Let's look at another example. I don't know how many I have. I have quite a few. Let's do the same thing for AlCl4 minus. What does this look like? It's Cl4 minus. This is a polyatomic ion. So let's do the Lewis structure. So I need the number of valence electrons, and that's going to be, well, I have 3 from aluminum, plus each chlorine has 7, so there's 4 of them, 4 times 7, plus this 1 from the charge. So 3 plus 28 plus 1, that's 32. Now, Al is probably going to be my central atom, so Al, okay, and I'm going to put Cl, Cl, Cl. The whole thing needs to be enclosed by square brackets, denoting that this is a polyatomic ion. Okay, now I gotta distribute stuff. So 32, I gotta make sure that this has 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Great. Now, oh, I have 4 of them. I'm sorry. Cl. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I actually distributed all 32, so it's done. So aluminum has 8, chlorines all have 8, and so this actually looks like this: Cl, Al, Cl, 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 like this. And this whole thing is that. Okay, now to determine the VESPR stuff, number of domains. Okay, so domains, you only look at the central atom, Al, and it's the number of single bonds, 0 single bonds, plus number of double bonds. Sorry, not 0 single bonds. What am I talking about? How many single bonds do we have? 1, 2, 3, 4. 4 single bonds, 0 double bonds, 0 triple bonds, 0 lone pairs. So this thing is 4. You look at the table again. Here, for the electron geometry is tetrahedral. So electron geometry is tetrahedral. Great. Now I want to look at my bonding domains. My bonding domains well, that's just single plus double plus triple. That's 4. And my non-bonding domains, that's the number of lone pairs. 0. So I look at this again. Bonding is 4, non-bonding is 0, so the molecule is tetrahedral as well. So this thing is tetrahedral. Molecule is tetrahedral. Okay, so that's how we do that. Let's look at yet another example. Why not? Let's look at I3 -1. It's a polyatomic ion of 3 iodines. So I have I3 -1. I don't know why it keeps doing this. Okay, sorry. So again, number of valence electrons is, well, each one of these gives me 7, and this charge is 1, so I actually have 22. And I have 3 I's, and I distribute these 22s around. Well, no, I don't. I make sure I have 8 on the wings. This is something new that's going to happen right now. We haven't done this yet. I have 8 plus 8, that's 16, and now I have 6 more. You have to put the 6 on the center no matter what. So I have 6 on the center. Check this now. This guy actually has, oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. He actually has 10 electrons around the central atom. Okay? And so what I'm actually going to be left with is this. Look at that. And this whole thing, I forgot, sorry, it's -1. Okay. All right. So now I got to look at the central atom and look at the number of domains. Number of domains for the central atom. Okay. Number of single bonds. 1, 2. 2 single bonds. Number of double bonds. 0. Number of triple bonds. 0. Number of lone pairs. 1, 2, 3. 3. 5 domains. So I look at my table. 5 domains. Now it's trigonal bipyramidal electron geometry. So trigonal bipyramidal electron configuration. Okay, now I got to look at my bonding domains. And that's just number of single bonds plus number of triple bonds and number of double bonds. So that's just 2 plus 0 plus 0, because I have 2 bonds. 2. Non-bonding domains, that's just how many lone pairs I have. Okay, so I have 1, 2, 3. 3. So it's a 2, 3. 3 bonding, 2 bonding, 3 non-bonding. So 2 and 3. So this thing is actually linear. See that? Ends up being linear. So this thing, so I3 minus is actually linear. Linear molecular geometry. So it's actually going to look like a linear molecule. Okay, perfect. So I hope that made sense. All right, let's look. Okay. let's look at HCN. So I told you I'm doing a bunch of examples to show you what's up. HCN. HCN looks like this. Okay. Let's say I already did the structure for you, so you don't have to worry about it. HCN looks like this. Okay. So I'm looking at the central atom, number of domains equals number of single bonds, 1. Number of double bonds, 0. Number of triple bonds, 1. So this counts as 1, not 3. Number of lone pairs, 0. Okay. Bonding domains. Bonding domains, okay, number of single bonds, 1. Number of double bonds, 0. Number of triple bonds, 1, 2. And non-bonding domains would be 0, because that's just the number of lone pairs I have. Okay, so I look at my thing here. My electron domains need to be 2. So that's here, 2. And I have 2, 0. Therefore, HCN is linear. Linear geometry all through and through. Let's look at one more example that I already worked out the molecular structure for you. Not the molecular structure, sorry, the structural formula for it. Here it is. Now what's up? Okay, either one of these is a central atom, whatever you want. This C or this C. Okay, so I'll look at this C, for example. Looking at it. Domains. Number of single bonds, 2. 1, 2. Number of double bonds, 1. Number of triple bonds, 0. Number of lone pairs, 0. So I have 3. And bonding domains, well, number of single bonds, 2. Number of double bonds, 1. Number of triple bonds, 0. And non-bonding domains, okay, 0. I have nothing. So I go look at the table of what's 3 and 0. 3 and 0. This trigonal planar. So it's going to be trigonal. Okay, that's it. That's great. All right, now let's do the last bit of it here. Sorry. And that's polarity. So symmetrical molecules do not have polar moments and are known as non-polar. So I know that CO2 is linear from all the examples we've seen. Linear stuff, definitely whenever you have a binary molecule, whenever you have a binary molecule that's the same, A2, B2, C2, whatever, these things are always going to be non-polar. They're going to cancel each other's weights out, okay? So only linear, trigonal, planar, tetrahedral, and octahedral can have symmetries. The other geometries are polar by default. So let's go back to all the examples that we just had. And I'm just going to recount to you what we discovered for all of them. So we said that HCN, we said that this is linear. So is this polar or not polar? Well, it could be polar, non-polar, if linear is allowed to be non-polar. By looking at C, this interaction is different from this interaction. Therefore, it's going to be polar. It's going to have some sort of a pole. It's going to be some sort of a being pulled from one way or the other. The electrons are not going to be equally dispersed throughout this thing. That's basically what polarity means. So it's not like the weight of the electrons in this bond is the same as the weight of electrons in this bond. There's kind of more here going on. So it's polar. Okay, so it's going to have some pole to it. All right, let's look at, let's see, let's look at I3 minus, which we already just did. And we said that this looks like this, if you remember. And it had this to it. And we denoted that this is trigonal bipyramidal electron geometry, but that the molecule is linear. So this is the molecule is actually linear. So since this is linear, it's on one line, one plane, it literally looks like this. It literally looks this way. This would actually end up canceling itself out. And so I have a nice even distribution of everything. Okay. Let's look at, what else did we do? Let's do one more here. Let's look at water. Water, we already said, is bent. If you look at bent, this is bent. Bent is not a symmetrical type of molecule. This is going to be polar. So that's how you'd identify polar, nonpolar, and so on and so forth, okay? Depending on the molecular geometry.